Hi, I'm Paul Kilgan from GK Tuition, and in this video I want to talk to you about inferential statistics. Now the question that I've chosen to go through here is 2018 Paper 2 Question 8. In the first part of this question, we're told that there's a company that is designing a new chocolate bar, and the average weight of this chocolate bar is going to be 4.64 grams, with a standard deviation of 0.12 grams. So we're told that if we take a sample of 10 bars, what is the probability that the average weight of those 10 bars will lie between 4.6 and 4.7 grams? Now again, I think it's really important that you draw yourself a diagram here so you understand what's going on. So that's what I've done here. I've drawn my normal curve. I know that the weight of these bars is normally distributed. I know the population mean is 4.64. I know the standard deviation sigma is 0.12. And n, the number of terms in my sample is 10. And I need to turn 4.7 into a z-score, and I need to turn 4.6 into a z-score. Now it would be very easy to use the wrong formula here. Look back at what we did in question 2. In question 2, when we had the English test and the maths test, to convert the result in the maths test into a z-score, we used the formula x minus mu over sigma, the standardizing formula. But we cannot use that here. This formula is x minus mu over sigma, where x represents one sample, one term. And that was just, we had one result in that English test, so we could convert one result into a z-score. But if you have a sample, you have to use this formula, which is on the next page in the log tables. It's x bar, which represents your sample mean, minus mu, which is the population mean, over sigma, which is the standard deviation, over the square root of n, which is the number of terms in the sample. So if you have a sample mean, in this case I'm really dealing with 10 bars, trying to figure out the probability that 10 bars will lie between 4.6 and 4.7. So I have to use this formula as opposed to the standardizing formula. As you can see, I've already worked this out. For number 1 here, I've used 4.6 as my sample mean, and the z-score in that case works out as minus 1.05. For the second solution, I've used 4.7 as my sample mean, and the z-score worked out, my z-score worked out as 1.58. Now that I have that, I can change the normal curve. I now have my normal curve now is the same as the one on page 36 in my log tables. Page 36, the mean of the population is 0, and everything else is referred to as z-scores. So actually, to finish this part of the question off, I need to work out the proportion of figures in any normal curve that lie within a z-score of 1.58 and minus 1.05. So let's go through that now. Okay, to finish it off now, I need to work out my shaded region here, which mathematically I want the proportion of figures less than 1.58 minus the proportion of figures less than minus 1.05. And that would leave me with just the shaded region in here. So I can read less than 1.58 straight off my log tables. It's 0.9429. In other words, 94.29% of all these samples would have a mean weight less than 4.7 grams. However, I then need to subtract the ones that weighed less than 4.6 grams. Or in other words, I need to subtract the probability z is less than minus 1.05. You cannot read a negative z-score off your log tables, so you have to change that to a positive z-score. So graphically, it's the easiest way to explain it. It's impossible for us to work out the figures less than minus 1.05. So instead, I'm going to work out the figures that are greater than plus 1.05. Clearly, this region to the left and that region to the right are the same, because it's a perfectly symmetrical graph. So rather than getting the probability z is less than 1.05, I'm going to get the probability z is greater than plus 1.05. So I change the sign of my z and I change my inequality. But you can't read greater than off your log tables either. Instead of the probability z is greater than 1.05, I'm going to get the 1 minus the probability that z is less than 1.05. To get rid of your greater than sign, it's 1 minus less than. And at this stage now, I'm happy with z is less than 1.05 because I can just read that straight off my log tables. It's 0.8531. So originally we said that 0.9429 is the proportion less than 1.58. And then I subtract the proportion that are less than minus 1.05, and I'm left with 0.796. In other words, 79.6% of figures in this normal curve will lie between 4.7 and 4.6. So your final answer there is your 79.6%. Okay, in the second part of this question, we're told that a research company surveys 400 people who tasted this bar, and that 324 of them enjoyed the bar. Okay, so that means 400 people were surveyed, my sample size is 400, and the proportion of them that liked the bar, the sample proportion is 324 over 400, which is 0.81. So in other words, 81% of the people who were surveyed enjoyed the bar. But now you have to put yourself in the shoes of the research company here. In an ideal world, if they actually wanted to figure out what percentage of people enjoyed the bar, they would survey everyone in the whole world who's tasted this bar. But let's say 1 million people have tasted this bar. It's completely impractical for them to actually survey 1 million people. So all they can do is take a sample size of, say, in this case, 400. Take a sample size of 400 and figure out what percentage of those 400 people enjoyed this bar. And in this case, it's 81%. Now, that doesn't actually mean that if they surveyed all 1 million people, that 81% of them would have enjoyed the bar. But it gives me an indication that if I surveyed all 1 million people, the chances are the percentage who enjoyed the bar is probably similar to 81%. So in my confidence interval, I take my sample proportion, the result of my sample, and then I add and subtract the margin of error. The margin of error represents the degree to which my 81% might deviate from the actual population mean. The degree to which 81% might differ from the actual mean if I surveyed all 1 million people, which from a practical point of view, I can't really survey 1 million people. So let's look at our formula here. Now this is not in your log tables, but bits of it are. So p hat represents your sample proportion. 1.96 represents the 95% confidence interval. Now, the only one on the Leaving Cert higher level course is 1.96, so you will never have, it'll always be a 1.96 there. And 95% level of confidence is a 1.96. But I want to talk to you about how I know it's the square root of p hat times 1 minus p hat over n. Because that's called the standard error. But there's two standard errors on the Leaving Cert course. And often students get a bit confused. The standard errors are sigma over the square root of n, or the one that we're using. Now, first of all, there's a couple of ways you can identify this. Sigma over the square root of n is the standard deviation of the square root of n. Well, there's no standard deviation in this case, which means you can eliminate that one because I don't have a standard deviation, so I can't use it. However, you might get mixed up and use your standard deviation from A part 1. So let's just think about this. This sigma over the square root of n is used for numerical data. This one is used for categorical data. Okay, so with categorical data, there's never going to be a sigma over the square root of n. There's never going to be a standard deviation. Categorical data is when you're collecting data and the answers are words, like yes or no, or colors, or something like that. Like, so for example, in this survey, if I was carrying out this survey, I might ask you, did you enjoy the bar? And your answer would be yes or no. Your answer is not going to be 12 or 13. It's going to be a word. So it's categorical data. So, and by virtue of the fact that they use the word proportion, it's a bit of a giveaway that you're using this one as well. But it's definitely not sigma over the square root of n, because that's for numerical data. Like, for example, in A part 1, we were talking about numerical data. We were talking about the weight of the chocolate bars. We had 4.64, we had 4.7, we had 4.6. So we had numbers, which means that if we were doing a confidence interval for the weight of the chocolate bars, we would be using sigma over the square root of n. But we're doing a confidence interval for whether or not people like the bar. So it's a yes or a no. So it's categorical data, so it's proportion. So just be aware that if you're dealing with numerical data, your confidence interval is more or less the same. The only thing is you have to change your standard error. So this is the result of my sample plus or minus the degree to which my sample might deviate from the actual population mean. Once you've identified that, it's relatively straightforward. But let's just look at this line. This line here, I've simplified out my margin of error. So the result of my sample was 0.81, or in other words, 81% of the people I surveyed enjoyed the bar. And this figure represents the degree to which my sample might be wrong. Based on the amount of people I surveyed and the result of my sample, I can figure out that the degree to which my results could be wrong is 0.038, or in other words 3.8%. So if I surveyed the whole population, let's say 1 million people in this scenario, my result would be at the very most 3.8% different from my 0.81. Which means that now notice I've introduced a new letter, I've introduced P, okay, and I'll talk about that in a second. It's the result of your sample plus the degree to which you could be wrong, the result of your sample minus the degree to which you could be wrong, which works out as 0.77, between 0.77 and 0.85. So if I surveyed all 1 million people, or whatever the size of this sample is, I can be 95% sure that between 77% and 85% of those people would have enjoyed the bar. Now you'll notice I've introduced P here. P represents the population mean, or the population proportion. So P hat is the sample mean, and P itself is the population proportion. This is the theoretical figure that technically for a research company would be impossible to find. This represents the proportion of people who would enjoy the bar if I surveyed every single person who's ever tasted it. Okay, so I hope that's making sense. Let's move on now and look at part B. Okay, for B part 1 here, we are given four different statements, and we have to state whether they're always true, sometimes true, or never true. Now, for the first one here, we're said for confidence intervals, for fixed values of P hat and N, an increased confidence level implies a wider interval. Okay, so if I want to be more confident about my results, my interval needs to be wider. That's what they're stating. So your confidence interval, we did it in the previous part of the question. Your formula is P hat plus or minus 1.96 times the square root of P hat times 1 minus P hat over N. Now they're telling me that P hat cannot change and N cannot change. P hat is fixed, N is fixed. So the only thing that could possibly change in this formula is your 1.96. Now it's important that you understand what the 1.96 represents. Look at the normal curve I've sketched here. In any normal curve, 95% of all of the data lies within a z-score of 1.96 and minus 1.96. In other words, 2.5% of the data lies outside that region, and 2.5% of the data lies outside that region. But they are called, in statistics, we refer to them as outliers. And in Leave Insert High Level Maths, our confidence intervals and our hypothesis tests, we always ignore the 2.5% at this end and the 2.5% at that end. Because statistically, it's incredibly hard to accommodate for what can be considered outliers or freaks in the context of the data. So the 1.96 allows me to be 95% confident. If P hat and N are fixed, if I want to increase my confidence level, let's say that rather than including 95% of the data, I now want to include 99% of the data. Well, obviously, if I need to include 99% of the data, my 1.96 number needs to get bigger. In other words, I need to accommodate for more of this normal curve. So the 1.96 needs to get bigger. If the 1.96 gets bigger, then the margin of error, a larger number multiplied by the square root of this, obviously this number gets bigger. So it'll be the result of your sample plus or minus a bigger number. You're adding on, in the last case we added on 0.038. We added on 3.8%, but if I wanted to be more confident, my figure would be bigger. Rather than adding on 0.038, maybe I'd be adding on 0.048. Or in other words, basically the margin of error gets larger. So you add on a larger number, you subtract a larger number, which means that your interval would get wider. So your interval gets wider because the number 1.96 has to get bigger. So the answer to the first statement was that it's always true. Okay, the second statement here says that as P hat increases, the standard error increases. Remember, P hat represents the sample proportion. Obviously, the sample proportion could be anywhere between 0 and 1. Okay, if I did a survey, my results could be anywhere between 0% and 100%, so 0 and 1. And you're working out if it goes closer, if the larger the number gets, as it gets bigger, does this number continue to get bigger? To be honest with you, it's very hard to explain this without actually doing B part 2. So in B part 2 we actually prove this one. In B part 2 we're going to use calculus, we're going to differentiate and get the maximum point and work out that the maximum point of p hat is a half. When p hat is a half, that is when the standard error is at its biggest. So as it increases from 0 to 50% or from 0 to 0.5, this value keeps getting bigger. But once it goes beyond that, it starts to get smaller. So to be honest with you, before looking at this one, I would look at the next part of the question where we do differentiation in it, because I realized that p hat is at its largest when it's a half. If p hat is a half, then the standard error is at its largest. So your answer to that is it's sometimes true, because as it gets closer and closer to 0.5, this value gets bigger, but once it goes beyond 0.5, it starts to get smaller again. So in that case, we're sometimes true. Okay, now third statement is as p hat times 1 minus p hat increases, the standard error increases. The standard error again is this. The standard error is a fraction. P hat times 1 minus p hat is the top of the fraction. If the top of the fraction gets bigger, then the number gets bigger. It's as simple as that. If what's on the top of the fraction gets bigger, then the standard error has to get bigger. So obviously if I increase the numerator, that one's always going to be true. Because all it is the top of the fraction is getting bigger. If the top of the fraction gets bigger, the number itself continues to get bigger. Okay, statement number 4. We can view this very similar to the one in statement number 3. As n increases, the estimated standard error of the population proportion increases. N represents the number of people you survey. But just if you think about it in terms of the fraction, the denominator is getting bigger. As the denominator gets bigger, the number itself must be getting smaller. So in this case, it's never true. But just think about it logically. N is the number of people that you survey. Obviously, the more people you survey, the more accurate your results will be. In other words, the standard error decreases. So as your population size increases, your standard error decreases. So that one is never true. In B part 2 of this question, we're asked to use calculus to find the maximum value of p hat times 1 minus p hat. Now you should realize that they're asking you for the maximum point. This is just like a turning point question. So you have p hat times 1 minus p hat. All I've done here is I've multiplied it out. I get p hat minus p hat squared. And I'm viewing that as that's my function. So my function is p hat minus p hat squared. And now I need to get the derivative. Remember, you can view your p hat as if it's your x, the way you would usually treat an x. The derivative of x is 1, so the derivative of p hat is just 1. The derivative of x squared is just 2x, so the derivative of p hat squared is just 2p hat, and there's a minus in between them. So I know that the derivative of this is 1 minus 2 times p hat. The reason that's useful for me is because I know that in order to find a maximum point or a minimum point, you need to let your slope equal to 0. Or in other words, you just need to let your derivative equal to 0. So I got my derivative here and I let it equal to 0, and I solved for p hat is equal to a half. In other words, a maximum exists when p hat is equal to a half. Now I want to refer you back there to, that's not my final answer here, but let's refer back to statement number 2 above. B part 1, statement number 2, when p hat is a half, that is the maximum value of your standard error. And that's why it's sometimes true, as p hat increases, the standard error increases as well sometimes, as it approaches a half. But once we go beyond the half, it starts to decrease again. The question didn't ask me in this case to find the maximum value of p hat. It asked me to find the maximum value of p hat times 1 minus p hat. So all I'm doing here is sub in my p hat. I know that this is maximized when p hat is a half. So you just sub in a half and your value works out as a quarter. The maximum value of this is a quarter. And that's my answer there. Now the last part of B says to hence find the maximum possible radius of a 95% confidence interval for a population proportion of a sample size of 800 people. So the sample size in this case is 800. It says the maximum possible one. If I want to get the maximum possible value, then my p hat needs to be 0.5. Because I've just worked out that to maximize the width of my confidence interval, my proportion needs to be 0.5. And they're asking you, obviously, if you're dealing with a confidence interval, you would be using the margin of error, not the standard error. The standard error is just the square root bit, but the margin of error allows me to be 95% accurate it's 1.96. So it allows me to accommodate for 95% of the data, ignoring the outliers on one end or the other. So in this case, you just sub in. I've got 1.96, the maximum p hat is 0.5, and the sample size is 800. If you plug it in, it works out as 0.0346, which as a percentage is 3.46%. So if you take a sample size of 800 in any set of data, and you're using sample proportion, the maximum degree to which your sample proportion could be wrong, the maximum possible error is 3.46%. Now I hope this video made sense. If there's anything you're struggling with there, then make sure you ask me in class or send me an email, and I'll try and explain it differently and I'll try and clarify it for you.